So in the last video, we looked at the compound angle formulae and we basically just derived them. And what we'll do in lessons is we will look at how to use them. But we're going to look at some kind of results, some consequences for knowing these. And they are the double angle, the half angle, and the factor formulae. So just a quick recap. I'm just going to look at sine a plus b and a minus b, and cos a plus b and a minus b. I'm not so interested in tan. Hopefully you had some fun attempting to derive that formula. But I'm actually more interested in sine and cos at this stage. So sine a plus b, or sine a minus b, if we remember, is sine a cos b, and the sign in the middle stays the same. So we can leave that as plus over minus, and our angle stays the same, but the trig function on it swaps around. And then in cos, we keep all the coses together. We're then going to switch the sign and then write an expression in sine. Okay, so the double angle formula, there are basically two key results, and what I'll do is I will basically prove them from the compound angle formulae, and then what we'll do is we'll box the ones that are the important bits, but it's really good for you to see how they're all linked. So we're going to get an expression in sine, and it's a double angle, so we're going for basically sine of two lots of something. We want to know about this. Now, we know something about that in the sense that we know how to expand that. We now know things about that. So if I let, let's put it the other way around. Let's let b equal a. See what happens. Well, we'd get sine a plus a. We can just expand that using our compound angle formula. So that would be sine a cos a plus cos a sine a. Now these are multiplied, so obviously we can just switch those around if we want to. And if we do switch those around, we're going to find that we've got two lots of the same expression. We've got two lots of sine a cos a. And so there is our first result. Sine of 2a is 2 sine a cos a. And that's just come from the compound angle formula. I think you should have a look at deriving cos 2a and tan 2a for yourselves. Just be warned, there are 3 different ways of writing this, so I'm just going to give you the results for this, and you can see if you can get yourself to those steps. So you should get to this point if you follow exactly the same method that we followed for sine. Now, we know, because we've been using it and because we've known it for C2, that cos squared a plus sine squared a is always equivalent to 1. Which means I can rewrite this expression as either 1 minus 2 sine squared a or 2 cos squared a minus 1. All of these 3, they're equivalent. So make sure you can use the trig identity that you know to get you to all 3 solutions, and make sure you can do this step between 2a and the result, cos 2a and the result. And then tan 2a, just use the formula in the formula book, shove a equals b, just like normal, and see if you can get to the result. We will go over them in class. Okay, the half angle formula just takes us on from the double angle formulae. So we are interested basically in knowing what sine of a over 2 and sine, what's sine, we've done sine already, cos of a over 2 might be. Now, to be able to prove these, we basically need something that isn't a halved angle. We need to know about a or something equivalent, and ideally what we'd like is the link between a and a over 2, or maybe we could have 2a and a, but some way that we can link up a halved angle formula to the original angles. And it just so happens, we've just looked at something that's very helpful to us. Cos of 2 theta, I'm going to pop it in theta for a moment for an important reason. And hopefully you've managed to get the results for that. If you haven't, pause the video, do it now. And I said there are 3 equivalent ways of writing it. I'm going to use 1 minus 2 sine squared theta for this one. This is really useful because I have a double angle and a single angle in the same equation, which means if I were to, and I think I might do, let theta equal a over 2, then 2 theta is going to go back to a, which is great because now I can write about these half angles just in terms of full angles. Really useful, obviously, because I don't always want an a over 2. I'd like to be able to talk about it in terms of a. So let's substitute these 2 things that we know now. So cos of 2 theta, when we've worked out that 2 theta is a, so cos of a is equal to 1 minus 2 sine squared theta. Theta is a over 2. Now, obviously, my half angle formula is hidden in amongst a whole load of other rubbish here that I don't really want, and actually what I'd like to be able to talk about is sine of a over 2. So let's rearrange to get that on its own. So 2 sine squared a over 2, just by moving it over it's become positive, is equal to 1 minus cos a. Again, I've just moved over that cos a. Right, sine squared a over 2 is equal to, what have I done? Oh, I've divided by 2, so let's divide by 2. And then the last thing I need to be doing is square rooting both sides, and I can do that because there's only one expression on both sides. So sine a over 2 is equal to plus or minus the square root of 1 minus cos a over 2. You should be able to derive cos a over 2 for yourself. You're just going to need to use cos 2 theta equaling 2 cos squared theta minus 1 instead of the sine squared theta 1. But that's why having all 3 of those equivalences for cos 2 theta is so useful to us. The last thing we need to look at are some bizarre little formulae in the C3 formula book called the factor formula. And these are, well, to be honest, when I was doing my A-levels, I never understood these, and I think I really missed out because they're really, really useful. And I've only discovered this in more recent years. The more maths I've done, I had to go back and kind of learn these because I never really got them at college. So don't be like me, don't create more work for yourselves later on, do them now. They look really, really weird. They look really weird. They look like you should be able to do things with them, that you would recognise bits and pieces from them. But you just can't work out how the heck you're going to get any information from it. But they're so useful when it comes to trying to solve or even just manipulate things like this. I can't add sine x and sine 3x. It's like trying to add like x and x squared. It's just not going to happen. But having a way of collecting these 2 terms together is just going to be so useful to me. So let's talk about them. Let's talk about them. Okay, I'm going to kind of start from somewhere else. Start from an identity or a formula that you know, and we're going to get to this expression. And then we will look at, well, actually, in fact, you could then work out pretty much any of the other ones in the formula book that you want. Completely up to you. So I'd like to look at, and I'm going to change the letters I'm using, but don't be fooled by it, it's the same thing. Sine x plus y, it's one of my compound angle formulae, and so let's expand that out. That's sine x cos y plus cos x sine y. And I'm also going to look at sine x minus y. So that's sine x cos y minus cos x sine y. Now, the left-hand side, just those are expansions at the moment, but I could deal with those if I needed to. I'm interested in seeing whether anything of the structure or anything else can be made to match the right-hand side of this expression here. I've just coloured in salmon. I've got two lots of sine of something, cos of something else. Well, there's my sine of something, cos of something else, and I've got two lots of them. If I add those two expressions together, and helpfully, if I add these two, this cancels with that. So let's do that. Let's have a play. Sine x plus y plus sine x minus y gives me sine x cos y plus sine x cos y. So 2 sine x cos y, and then cos x sine y minus, because we're doing plus minus, cos x sine y, and they've disappeared. Okay, still looks nothing remotely like what I want, except for I have my two. I have a sine of something, and cos of something else. It is something different because this one's a plus and this one's a minus, so we do want different things here. And actually, do you know what? I'm going to force them to be those things because I don't like these x's and y's when I want a's and b's. So let's let x equal a plus b over 2 and y equal a minus b over 2. And let's substitute that into everything we can. So sine of x, so a plus b over 2 plus y, a minus b over 2, plus sine of a plus b over 2 minus a minus b over 2 is equal to 2 sine a plus b over 2 cos a minus b over 2. And do you know what? I think we might have done it. Move this away. So that's a half a plus a half b plus a half a minus a half b gives me 2 halves of a, which is just an a. And then we've got a half a plus a half b minus a half a, so that's gone, minus a half b. So we've got b over 2 plus b over 2 is just b. And that's equal to 2 sine a plus b over 2 cos a minus b over 2. Done it. Brilliant. So a bit of a fiddly, a little bit sneaky, this is a bit sneaky here, proof, but actually nothing new. We've just used our compound angle formula again. But as I said, they're incredibly useful. And once again, it's all about, can you recognise them? So in class, what we're going to do is we're going to make sure you've proven everything else. Obviously, there are 4 of these factor formulae if you look in your formula book. And it would be good for you to have practiced deriving them by practicing deriving all of them. And then we will look at how to use these formulas. So you've got the compound angle formula, you've got your double and angle and factor formulae. We'll just have tons of practice about recognising them, using them, and hopefully you'll be feeling pretty good to go on trig by that point.